Hello everyone. This is Gayatri Priya, Assistant Professor in the Department of ECF RMD Engineering College. In today's session of Electron Devices and Circuit Theory, we are going to discuss about early effect or base width modulation. So before getting into this early effect or base width modulation, let us see the various BJT configurations. So BJT stands for bipolar junction transistor, right? So bipolar in the sense it will be having both the uh, majority charge carrier as well as the minority charge carrier, right? Actually, this is going to be the two diode analogy of the BJT, right? So if we connect to back PN junction diode that form a transistor, right? So here you could see this N type, so this cathode will act as the N type and this cathode will act as the N type, and these two anode are interlocked with each other and it will be acting as a P type material, thereby creating an NPN transistor. Similarly, a PNP transistor can be formed by just connecting two diodes which are in the reverse. Okay, so this is PNP transistor. The center part is always taken as base, the left hand side is emitter, and the right hand side is going to be the collector. So obviously the three terminals are emitter, base, and collector. The three transistor currents are emitter current, base current, and collector current. Right. Here we have been given up with the PNP transistor. So and this going to be the symbol of your PNP transistor. At your emitter, you will be having a pointer. If the pointer is pointing, okay, so then it will be constituting the conventional current direction, right? Okay, so here we have taken a NPN transistor, that is a P-type material is sandwiched between two N-type material. So here is one NP diode and this is PN diode, thereby creating two junctions J1 and J2. The center one is base, the left is emitter and the right one is collector. Obviously, the current present here is emitter current, the current present over is collector current, and this is the base current here, right? And similarly, the junction voltage in between emitter and base, we will be measuring VBE or VEB voltage. In between collector and base, we will be measuring collector base junction voltage, right? And here we have been given up the connection setup of a common base in both N channel as well as the P channel BJT, right? Here you could see this is the emitter terminal, base terminal, and this going to be the collector terminal. So obviously this is going to be your N type and this is your P type and this is going to be your N type. If N is connected to negative polarity, P is connected to positive polarity, then that is called forward bias. Similarly, if N is connected to positive polarity and P is connected to negative polarity, that is reverse bias. Always the input junction is forward bias and the output junction is reverse bias, so that we can have a proper feasible operation of a transistor, right? If both the junctions are going to be in the forward bias, then that is called saturation region. Okay, saturation condition, that is the current will be tremendously increasing. If both the junction input and output are going to be connected in the reverse bias, then that is called cutoff region. Under the cutoff region, the current is going to be zero. So the same thing is given for a PNP transistor, right? So here the input current is going to be IE, output current is IC. Ratio of output current to input current is called current gain, or simply we can say amplification factor. Since this is the current gain of common base, we can mention it as CB current gain, or we can simply mention it as current amplification factor. We know that IE equal to IB plus IC, right? Where IC can be written as, using this relationship, IC can be written as alpha times of IE. Okay, therefore IB is equal to 1 minus alpha into IE, right? And these are the current amplification factor relationship between common base, common emitter, and common collector. Alpha is going to be the current gain of your common base transistor, and beta is for your common emitter transistor, gamma is for common collector configuration, right? Alpha is equal to IC by IE, beta equal to output current IC by input current IB. Similarly, gamma is output current IE by input current IB, right? So we are having the generalized equation IE equal to IB plus IC. So dividing the entire equation by IB. After simplifying this, we are getting the relationship between alpha and beta as alpha is equal to beta by 1 plus beta. If I want to express beta in terms of alpha, then that is equal to alpha by 1 minus alpha. And gamma is nothing but IE by IB. That is, we are just going to multiply, okay, these things by IC, and gamma becomes equal to 1 plus beta, or simply we can say 1 minus alpha, right? And this is going to be the input characteristics curve of your common base configuration. The input current is IE, that is taken along the y-axis. Input junction voltage is VEB, that is taken along the x-axis. At constant output junction voltage, that is VCB, right? Here, what happens whenever I'm increasing this VBE, okay? So IE will be remaining as 0. That is, it will just resembles that of your forward bias of PN junction diode. Once it reaches the cut-in voltage, then only it comes into conduction. The current flow will be produced. Okay. So whenever I keep on increasing this output junction voltage, we could see the curve is growing inward. Okay. This is not in the case of common emitter. If we increase the output junction voltage, the curve will be growing outward. Whereas in case of common base, the curve is growing inward, and that property we are going to discuss in this session, right? So Ri is going to be the input AC resistance, that is equal to variation in the base emitter junction voltage to the variation in the emitter current. Okay, so that is going to be the reciprocal of slope, right? This is the input characteristics. Okay, and coming for the output characteristics, here the output current is going to be IC, right? And the output voltage is going to be VCB, and for constant IE input current we will be measuring up this, right? Here you could see we are getting some sort of current conduction even the negative VCB, that is the output junction voltage is kept negative, even then we are getting some current flow, okay? And this region is called the ohmic region, okay? Or why? Because in the sense only in this region the Ohm's law is accepted, that is depending upon the voltage the current will be varying proportionally, and these regions are called as the saturation region. Why? Because in the sense the current has been exhausted, it is maintaining a constant value, and the region below input curve equal to 0 is called cutoff region. So in cutoff region, both the input and output junction are reverse bias. In saturation region, both the input and output junction are forward bias. Whereas in your ohmic region, okay, so what happens? The input junction is forward bias and the output junction is reverse bias, and this going to be the output AC resistance R naught, that is equal to small variation in the output junction voltage to small variation in the output current IC at constant input current, right? Coming to the main thing, that is your early effect or base width modulation effect. The previous output characteristics we have mentioned that we will be getting the current flow, that is the ohmic region, even the output junction voltage is reverse bias. That is because of this early effect. Okay, now let us see what happens for lower values of VCB, right? So we know when compared to base, emitter collector is heavily doped. When compared to base and collector, emitter would be heavy doped. Okay, so therefore what happens in the sense, depending upon the doping concentration, emitter is very high, base is very very low um, doping will be there, and the collector will be a moderate between the emitter and the base terminal. So already we know that the depletion width will be penetrating deeper whenever the doping concentration is less. So compared to emitter, the base is having a lesser doping concentration, and obviously the penetration of the depletion width nearer to this base will be deeper when compared to that of the emitter. Similarly, compared to the base, okay, the collector is highly doped. Therefore, this depletion region will be narrow when compared to that of the base, right? And this is going to be the effective base region where we will be having the surplus amount of free charge carrier that can be under movement. We know the depletion region is devoid of free charge carriers. It will be having only the immobile ions. Okay. So coming to the high value of VCB, I'm increasing the collector based junction voltage. If I keep on increasing the collector based junction voltage, what happens in the sense? The charge carrier will be more. Okay. So we have told the input junction is power bias and the output junction is reverse bias. Then obviously what happens, the depletion region will be penetrating very very deeper inside the base region, thereby the effective base width is reduced. Okay, can you see over here? Here you are having the base width to this region, whereas here the base width is reduced if we increase the collector base junction voltage. That is, the effective base where we'll be having surplus amount of free charge carrier under movement is being reduced, is being modulated, is being changed if I keep on increasing the collector based output junction voltage. This process is called base width modulation, and because of this property alone, we had the ohmic region well before the VCB is equal to 0 volt, right? And you could see this is the effective base width. Okay, it has been become very thin, and this is the depletion region at the input junction, and this is going to be the depletion region at the output junction, that is collector base junction. So by doing so, what happens? The base width, effective base width is reduced in a very larger extent. Hope you understand these sessions. Thank you for watching.